This year's Ultimate Goal game has required us to use lots of math and physics compared to previous year's games. Our team used basic physics concepts as well as RPM equations to solve the path and trajectory of the ring. In this video, we'll be walking through all the steps as to how we derived our own equation. Using these three big equations of mechanical physics, we were able to derive our equation. V is the final velocity, V of O is the initial velocity, A is the acceleration, T is the time interval, and D is the displacement. The type of movement we're dealing with is projectile motion, which is the motion of an object thrown or projected into the air, subject only to the acceleration of gravity. The height of the ring is affected by the acceleration due to gravity, while the length of the ring is affected by the acceleration of your output system, which in this case should be flywheels. Other factors such as air resistance must also be taken into consideration. However, that can be dealt with after our equations are formed. The angles required for a robot can be determined with the horizontal velocity equation and the vertical acceleration equation. Our first step is to calculate the angle of the launch mechanism as well as the velocity required for the ring. By substituting our equation for vertical acceleration of gravity into the third basic equation of mechanical physics, we get our equation for vertical acceleration. Now that we have our movement in the y direction, we substitute our equation into the first basic equation of mechanical physics to get our movement in the x direction. Finally, we can simplify both of these so that we can work with both x and y directions together instead of separately with some trig functions. The velocity of the ring should be the vector sum of the ring velocity in the x direction and the ring velocity in the y direction. Our final equations give us the raw velocity required for the ring at different angles of launching. At this point, we will need to calculate the amount of rotations per minute your flywheel or wheels will need to generate to get the ring to a certain velocity. We do this by calculating the energy required to launch the ring, the force used by the spinning wheel, and the amount of energy lost due to friction. The design of the flywheel causes to use half the energy generated by the rotations per minute into spinning itself, and the other half goes into launching the ring. In this case, our ring weighs 30 grams. This is the equation used to calculate rotations per minute. We can now incorporate this equation into the raw velocity equation we derived before. Using algebraic operations, we can simplify the equation to give us the RPM of the motor required directly for the ring so that can all be calculated with one equation instead of three. Now, the best plan of action is to put your equation into a Google spreadsheet, so to be used as a calculator. Here you can calculate and store multiple angles, RPMs required, and create graphs as well. However, this will only give you a good estimate since we disregarded air resistance to make our equation easier to work with. With more testing, recording, and adjusting, your robot will be able to consistently hit your targets. Thank you for watching.